Hey, before we get started, I have one small request for you. I'm trying to learn more about you and what you want from these videos. So I made a survey, the link is down below. Should take just a few minutes, would love it if you could fill it out. Thanks, and let's get on to the video. Hi everybody. So today I want to talk about envelope following and gate detection. And the reason I'm talking about it is because I have been doing a project on the side this year with a friend that I hope I will be able to share more details about in the near future. But this device required basically that we listen to an audio input and be able to identify sound events, basically, by determining when the event begins, meaning when the sound begins, and when the sound ends. So I had to work on this algorithm that would be able to do that effectively without giving us false positives or failing to detect events that we want to detect. So today I'm going to walk through this patch that I made in Gen that accomplishes that purpose. So let's do it. Okay, so first we'll actually start with the basic principles of gate detection. And somebody actually asked about this in the Max Discord very recently, and I kind of gave the basic pointers. So here we have just a microphone input from my voice. And the very first thing that we want to do is create an envelope follower, which is just going to give us a signal that represents the sort of contour of the amplitude of this signal. And as we know, audio signals are bipolar. They oscillate between 1 and -1. So the first thing that we need to do is make that signal positive or unipolar. So first we'll just take the absolute value. And if I talk, you can see that now we're only getting positive numbers. And then the second thing that we need to do is basically smooth this out. And the way to think about this is like low pass filtering. We're just going to be removing some of the oscillations essentially in this signal and force it to just give us the general shape of this waveform. So for that, we'll use the slide object. And slide takes two arguments, which is the amount to smooth out the signal in the up when the signal is rising, as well as the amount to smooth it out when the signal is falling. And for this particular purpose, we can just use the same value for both. And this value is in samples. And we can think of this basically as the amount of time that it takes for a change in the signal value to kind of be realized. So if I put this in and I move my scope down here, then you can see we're getting this nice smooth, and I have to talk a little bit louder. Maybe I can turn this up a little bit. I'll just give this little gain here. So hopefully now, yeah, there we go. We can see a little bit more. So we're just amplifying it so that you can see what's going on. So now we have this wave, and now we can basically tell this thing, okay, tell me if the signal value here crosses some threshold like 0.1. And so if the signal is above 0.1, then we're going to open the gate, and if it falls below, then we will close the gate. And so we can see the results there. Now, one thing you notice is that, this still tends to bounce around a lot because the signal will kind of momentarily dip below 0.1. And so the gate should just be consistently open here while I'm talking, but it tends to jump around. So there's a few things that we can do. Obviously, we could change this threshold, but then we risk creating false positives. If I talk quietly, then we're not going to get anything, right? We could also change the smoothing. So if we wanted to, maybe smooth this out more, then maybe that allows us to get a better result. And we go back to 0.1. Maybe that gives us a better result, but still, it's a little bit temperamental. So what I want to talk about are some of the strategies that you can use to make this kind of system work better, which are strategies that I used inside of the device. So the first one is to use, rather than a threshold in this amplitude value, to use decibels. And the main reason for that is just that it makes it easier for us as a human being to control the device, because the relationship between this actual amplitude and what we perceive as humans as the kind of loudness is not linear. So when we think about it in decibels, then we can just make it easier to control this. The second and more important thing is introducing this concept of a hold time. So this is basically an amount of time that the signal needs to consistently remain above the threshold in order for us to open the gate, and then the amount of time that we need to be below it to actually close the gate. So when we initially cross it, we'll start this timer basically for however much time, like maybe 100 milliseconds, and say, if this signal never crosses back below the threshold for that amount of time, then we're going to say, yes, we have a new gate here. We have a new sound event. Then it's basically waiting for that signal to cross below the threshold. And when it first crosses below, it's going to do the same thing. It'll start a timer and say, okay, it is not until this timer ends that I will consider this event to be over. And the timer gets reset if the signal ever goes back up above the threshold. So it's just a way to kind of force some of these oscillations, some of this kind of jitteriness that we see here in the gate detector to go away, because we're adding a little bit of, I guess you could call this hysteresis. Maybe that's not totally the right word, but it's that basic idea of like, it wants to stay in the state that it's generally in, and you kind of have to like be above or below the line for a while in order for it to change that state. So let's go to the patch here in Gen, and I will remove this for now. So, let's actually do this. So, actually that's fine. We can multiply for 2 for the purposes of the waveform, but the signal actually flowing into the Gen patch is not amplified. We'll set that to 0. So we have a few parameters here. We have the smoothing amount. We have the attack threshold, the release threshold. So this is just the threshold required to create a node on, the threshold required to create a node off, and then those hold times. And then on the output, we have the gate itself. We also have this stage output, which is basically visualizing the kind of function of the gate generator. And then we have the envelope itself. So to talk a little bit more about this stage idea, so we can think about the gate detector as having 4 stages. So the first one is there is no sound, or more accurately, the sound is below the attack threshold. So we're waiting for the signal to cross the attack threshold. Once it does, then we're in stage 2, or I started counting from 0. So stage 0 is no sound. Stage 1 is we've crossed that attack threshold, and that timer is running. So this attack hold MS timer is running. And when we get to that, if during that period, the signal drops back below the threshold, then we go back to stage 0. And again, we're just waiting for the signal to cross that attack threshold. Once we finally get through that timer, the signal is consistently above the threshold. Then we move to stage 2. And at this point, we're waiting for the signal to cross below the release threshold here. And it's the same idea. Once it crosses below the release threshold, we start a timer. And if the signal remains below the threshold for that amount of time, then the gate is over. But if it ever crosses back up above the threshold, then we are back to stage 2, and we're waiting for that downward crossing again. So stage 1 is no sound. Stage 0 is no sound. Stage 1 is we've crossed the threshold, but we're waiting for it to be confirmed. Stage 2 is we're waiting for the downward crossing, and stage 3 is we've got a downward crossing and we're waiting for that to be confirmed. Okay, so let's get into the patching. So we have these kind of 4 sections, and one of the reasons that I wanted to talk about this patch that I thought it'd be interesting for all of you is that it kind of uses history, and it uses history in interesting ways. So we can kind of break the patch up into these different sections that have different functions, and they're related to one another. They talk to each other, but we're using sends and receives and history objects to kind of to separate them from one another. It makes it a little bit easier to follow the patch. So down here we have the definitions for some of the parameters, the hold times, and then up here we have the thresholds, and then here we have the envelope follower. So we get the input, which is the signal that we're analyzing, and we expose it to the envelope follower, which is very, very simple. Basically, all that we're doing is exactly like I showed you in MSP, taking the absolute value and then applying slide. And then we just have a simple mapping that's going to map the slide, the smoothing value on the range of 0 to 1 to the range of 10 to 5,000. And that's just something that I figured out through trial and error. And as I use this device more and more, I may fine-tune this a little bit based on what I learn. So once we've smoothed out that signal, then we're getting something that's looking like that envelope smooth signal that we had before. So it's unipolar and it's smoothed out. From there, we can then evaluate the crossing of the thresholds. So we can say anytime that we have a positive crossing of the attack threshold, then we will get an impulse right here. So we say, is the signal currently above the attack threshold? If that state of being above or below changes, then we'll get an impulse. And if that if it changes in the positive direction, meaning the signal changes from being below the attack threshold to above the attack threshold, then we'll get a 1. If it's going in the opposite direction, we'll get a -1. So we get a 1 here when we go from below to above. And then on the other side here, we have the exact same thing for the release threshold. So we're basically just tracking these changes in the state of the signal relative to those thresholds. The next thing then that we do is we feed the results of those signals into a selector object. And that selector object, it basically turns on only one of these inlets. So based on some number that we send into the first inlet, one of the remaining inlets is activated and flows to the output. And the stage that we are currently on, whether that's 0, 1, 2, or 3, is what opens up the appropriate inlet and allows us to basically monitor for the thing that we care about at that point in time. What are we waiting for? Basically, when you're in stage 0, you're checking for a positive crossing of the attack threshold. If you're in stage 1, you're looking for a negative crossing of the attack threshold, because that would mean that you're going back to stage 0. If you're in stage 2, you're looking for a negative crossing of the release threshold, because that will advance you to stage 3. And then when you're in stage 3, you're looking for a positive crossing of the release threshold, because that would send you back to stage 2. So hopefully that makes sense, and I'll perhaps demonstrate a little bit in the main patch where we have this nice ramp. So if I increase the hold time, let's say to 1,000 milliseconds, so 1 second, and I stop talking, you'll see that this stage line will go down to 0. And then if I make a short sound, which I'll do in just a moment, you'll see that the diagonal line will start to rise, but then once I stop making sound, it will drop again. So let's try that. Hi, hi, hi. So you can see that we move from stage 0 to stage 1. So stage 1 is that first rising diagonal line. But then because I didn't give it enough time, the signal crossed back below the attack threshold, it went back to stage 0. Then similarly, once I've actually made it through that process, so now we're there, if I, sorry, this is a bit challenging. Let me lower this back down. I'll make this 100 again. So now this is open, and then if I stop talking, you'll see that downward line begin that's trying to close the gate. But if I start talking before the downward line completes, then I'm back to stage 2, and the gate is still considered to be open. And the gate signal is this top one. So you're seeing that happen a little bit, where anytime I pause, it starts to decline. But if I don't pause for a full second, then the gate isn't actually over. But if I do pause for a full second like this, then that's the end of the gate. So that's the idea. We're in terms of us looking for these different crossings at different times. So, how do we actually get this stage, right? Like, how do we know what that is? So we have this concept called advance. So when these triggers happen, and there are, as we've talked about, there are these 4 triggers, but then there's also 2 more, which are the timer completing, and that's what this section is. But basically, when those events occur that we care about, the crossing of the thresholds or the completion of the timers, we get an impulse that goes to this advance send and receive that flows into this accumulator that's basically just going to tick us along on this set of stages from 0, 1, 2, 3, and then back to 0, because we have a 4 here in this modulo. If we get a negative value, which is possible from these impulses, because if the signal value is going from, let's say, above the attack threshold to below the attack threshold, then we'll get a -1 over this particular patch cord. Then the advance impulse, which is here, can go in the opposite direction, so that we go from, in that particular case, stage 1 back to stage 0. So that's, I think, a pretty nice design, right? We're identifying these crossings of the thresholds. We're monitoring for the one that we care about at any given point in time based on our stage. And then we're using the signal direction of the kind of state of that threshold to move our stage forward or backward. So that's what this section is doing. And this is actually where the gate is evaluated, because basically if we're on a stage that is after 1, so if we're on 2 or 3, then we consider the gate to be open. What this means, of course, is that the attack time kind of delays the beginning of the gate, right? So if we go back to the main patch and I turn this way up, and then I start talking, you can see that the gate hasn't actually opened, right? So there's a little bit of tuning here. You're going to get better performance at kind of ignoring like momentary tiny sounds that you don't want to count as gates when you set this higher. But the trade-off there is that you don't detect those shorter sounds, and you also have this delaying of the beginning of the gate. So you really want to sort of set that so that like the minimum, it's relatively short, and long enough to prevent kind of like momentary clicks and stuff from being registered as gates, but not so long that you're getting these other negative side effects. Right, and then so yeah, stages 2 and 3 are considered to be the gate is high. Okay, so let's talk about the last bit here, which is the timer. So again, we have a selector, which is looking at what the current stage is. And based upon that, we're taking in some values that are going to feed into this, this ramp generator. So this is basically just a simple circuit that works actually a lot like the MSP object ramp tilde, where we take our hold time, and if that value is not -1, because in the case of stages 0 and 3, we don't use this ramp at all, so we just want to deactivate it. So the way that I did that was just passed a -1 in here, which is just a way to kind of like easily see like it's turned off when we're in stages 0 and 2, which are the, you know, the flat parts of the stage spectrum. So if this value is -1, then we're passing 0 into this accumulator, and we're just not accumulating anything. We just have a flat line. If the if we're in stages 1 or 3, then we do have a hold time, and because that value is not -1, then we are going to activate this. So we'll add 1 for every sample within this gen patch. And we're going to build an accumulator that it basically counts from 0 to the number of samples that represents this hold time, release time, or attack time, or whatever it is. because we convert those milliseconds to samples. We then also, each time we have an advanced trigger, we reset the phase of this accumulator. So if any of this stuff is confusing to you, you should go watch some of the other videos that talk about this concept of how to build accumulators. And there's kind of two general types that we might build in Gen. One is kind of a phaser style that loops indefinitely, and that would typically use wrap in this location. But this kind that uses clip can be really handy in these cases where we want a one-shot ramp. One place where I talk about this whole bunch is the sampling series. So you can go watch those videos if you haven't seen that already. But basically, when we hit the end of the ramp, in other words, the value coming out of the ramp is equal to the length of the ramp time, then we know that that ramp is complete. And we have a little bit of delay in here just to prevent feedback within the max patch. But then we send an impulse, a positive impulse that's going to advance, again, our stage counter to the next stage. We also then have a little patch here that just handles the visualizer to make it easy to see what's going on this kind of second scope here. So that's all this is just really just for the visualization purposes.